mouse disappears, things don't work. So yeah, I was asked to talk about infinity, which is a topic I've talked about a few times to young kids and old people. Apparently I don't have an infinite amount of time to do this, so I'll be quick. It's a pleasure to be talking at the CRM inauguration, and apparently CRM is tied for the 117th best mathematical acronym. I don't know what the top one is. Mouse is gone. So the talk is essentially about this question: what is infinity? I remember as a kid bringing this word to show and tell, maybe in year one or something, and I think I was told by my dad that infinity is the biggest number. But we all sort of have an intuitive idea of infinity. That's what my son thinks of infinity as, up on the left, an endless supply of fun balls. We probably all imagine an endless supply of money, but a lot of us are academics and identify more with the middle version of infinity. That's fine. But what I want to talk about is an idea that goes back to a famous mathematician, Hilbert. If you think about hotels, there are some big ones on this planet. As far as I know, the biggest one is this one here, I think in Moscow, with thousands of rooms. But Hilbert imagined a hotel with infinitely many rooms, so more rooms than any number, so it just goes on forever. And here's how a mathematician represents a concept like that. All that matters is that there are infinitely many rooms, one for each number. And Hilbert's story involves a day where all of the rooms were full. And along came another person who was sad to discover there were no rooms left. And I hope this is going to work. No. So I'm going to have to do this and see if I can do that. Mouse again. All right. So there's a few videos in this, but we'll see how it goes. So the guy goes to room 1, sees there's someone there, sees there's someone in room 2. And by the time he gets to room 9, it's safe to assume that all of the infinitely many rooms are full. So he goes to the first one, manages to get the guy out, and so his problem is solved. But now we've got someone else missing. The red guy is not stupid enough to come out, so he tries number 2. And now his problem is solved. He's got a room 2. But you can sort of see that no matter what you try, you just can't get this extra person in. Okay. I can't even remember doing this. So anyway, the hotel proprietor ends up coming out with a clever trick, which is to ask everyone to come out. So this should all happen at once, but I don't have that technology. Everyone comes out, and then the red guy goes into room 1. Then the guy who was previously in room 1 goes into room 2. The person previously in room 2 goes into room 3. Okay. This also should happen immediately. So you can actually fit one extra person into a completely full hotel. And that illustrates the first line of this theorem, which is that infinity plus 1 equals infinity, something that's not true for any ordinary number. Now I'm told that we have to be fairly quick, so I'll keep an eye on my clock. I don't think I have to convince you that if there were 3 people, you could still fit me in, so I'll skip this video. But infinity plus 3 is infinity also. And in fact, if you tried to squeeze any number of people in, you could do it just by asking everyone to shift up that many places and thereby free a few places at the start. The next question is, what about infinity plus infinity? And this is what happens when an infinite bus arrives at the hotel. This is clearly a photoshopped picture because there's no such thing as an infinite bus. But here's an even more fun picture that I found. Google tells me that she's saying, meet me at midnight at room infinity. Okay? And clearly there's no actual room infinity, there's just infinitely many rooms, they go on forever, there's nothing at the end. Anyway, it'll be fun. All the good pictures about this are in French, by the way. So what happens if an infinite bus arrives? Well, there's this clever trick where we shuffle the two together. So everyone comes out again, and then we just go black, red, black, red, black, red, black, red, and everyone fits in somehow. So what happens is that the black people are all in the odd numbered rooms and the red people are all in the even numbered rooms. You get the picture. So infinity plus infinity is infinity. Another way to say that is infinity times 2 is infinity. Again, you can all work out that you can shuffle three decks of infinitely many cards together, so infinity times 3 is infinity. Infinity times anything is infinity. But what about infinity times infinity? Here we've got infinitely many buses. How do we fit all of these people in? Well, this is a trick that goes back to another famous mathematician called Cantor. His trick was this. Instead of looking at this as infinitely many lines, each of which is infinitely long, tilt your head 45 degrees to the left and see this as a pyramid. There's still infinitely many lines, but the first line has 1 person in it, the second line has 2 in it, and 3. So you can line all of these people up just by putting the first line up, then the second line up, the third line up, but now the lines are only finitely long. So number 1 goes up, and 2 and 3 will go up. And you can see that all these red people will end up in a single red line, and then we can just shuffle them together like we did before. So I'll have to skip the exciting end. So infinity times infinity is still infinity somehow. Or phrased differently, infinity squared equals infinity. I couldn't draw or find a picture of infinitely many car parks, each with infinitely many buses, each with infinitely many people, but if you can imagine that, infinity cubed is infinity. I can't even describe what it means to say that infinity to the n is infinity in terms of buses and car parks. The next question is, what is infinity to the power of infinity? And I've definitely got no time for this, but the only mathematical proof of this talk will just be whizzed past your eyes. And I hope that you believe me that infinity, the power of infinity is greater than infinity. This is the most surprising thing of this theorem. And hopefully you recognize the odd one out. The only thing that doesn't have the answer of infinity. So 2 questions are raised here. First is, how can something be bigger than infinity? And the second is a variation of that question, is what on earth is actually going on. So I'd like to just very quickly summarize a couple of things that we can say about this. This is the last line of the previous theorem. Turns out that you can talk about infinity to the power of infinity to the power of infinity. We could have a tower of 4 infinities, or 5 or 6 or 7, each getting bigger and bigger. Okay? So you have an infinite list of infinities, but there's something bigger than all of them. And there's something bigger than that, and there's something bigger than that. There's never an end to the chain of infinities. So because we don't like to write things like infinity to the infinity 19 times, we have these symbols for them. Hebrew aleph is the letter there. Aleph 0 is the smallest, aleph 1 is the next. They go on forever, and there's no biggest one. But here's a mystery that we don't know about. If you're reading the colors, I didn't color infinity to the infinity red, even though I colored aleph 1 to the red. Colored aleph 1 red. We've got these 2 second terms in the 2 lists that I've got there, but we don't know whether those terms are the same. But what we do know is that we'll never be able to know that, in the sense that you can't prove that it is the case, and you can't prove that it's not the case. So we're forever stuck not being sure about that. And that's the end. There's a few other paradoxes I think are good fun, and a few names of mathematicians and philosophers that you can consult about this topic. Thanks very much.